Hello, and welcome back to this talk about diffusion, or specifically about how to pre-process diffusion data in order to correct for distortions and subject movement. And if you remember from the previous episode, we concluded with saying that we need to estimate one of these, i.e. a susceptibility-induced off-resonance field per subject, and one of these, i.e. an eddy current-induced off-resonance field per volume. And what we're going to do in this episode is we're going to look at the tools that we have in FSL for estimating those two, well, there's more than two for the eddy current, but in principle those two fields. So first of all, how topup works, very briefly. So assume that we have two images acquired with different phase encoding. And for this argument, assume that we know what the off-resonance field is. And in addition to having these two images, we obviously know how they were acquired. So this was acquired with positive phase encode blips in the y direction. This was encoded with or acquired with negative phase encode blips in the y direction. So given that we know the acquisition parameters, we can then translate the off-resonance field into fields of displacement of intensity, i.e. displacement fields. These can then be used to correct the distortions. But the problem is we don't know the field, and that is what we want topup to calculate. And so what topup does, it starts out by guessing a field. So it guesses, when it starts out, it has absolutely no idea. So it's going to guess that the field is 0 everywhere. From that, it calculates the displacement maps. They are also 0 everywhere. Then it uses those displacement maps to correct the images, which in this case means not doing anything to them at all. And then, important what it does, it calculates the sum of squared differences between the two images. And in this case, we're going to get a very large number for the sum of squared differences between the two images. So based on that very large number and based on the way that this difference image looks, it can then come up with a better guess for an off-resonance field. So it then guesses this field this time, and we now translate this field into displacement fields for the two different acquisitions, and we use that to correct the images, and now we have a better difference map, or a smaller sum of square differences. And we just keep guessing and guessing, each time updating the guesses using this difference map until we have the best possible field, i.e. the field that gives us the smallest possible sum of square differences between the two corrected images. Now, obviously, I made this sound very simple, and the trick here is how to use this difference field in order to update your guess or your guesstimate of what the field is. I'm not going to go into those details, just say that it's a Gauss-Newton updating scheme, and it's proven to be quite robust and works quite well. So that's topup. The next thing we're going to talk about is how we are estimating all those different eddy current induced fields for the different images. i.e. we're going to talk about how a software called eddy works. But before we get to that, we're going to have the world's shortest course on image registration. And it's a course that consists of only one slide, and this is this. And essentially what I'm showing you here is an example of two images, one in red and one in blue. And the allowed transformations in this case is that you can translate one relative to the other in the y direction, or in the x direction, or in both directions. And so that is essentially our transformation model, our space of allowed transformation. And what we also need is an objective function or a cost function, and the cost function is simply the negation of the objective function and vice versa. So it's a function whose maximum or minimum tells us that now the images are optimally registered. And what we can look at here, so again, this is This is the negation of the sum of square differences between the images, and we can see that when they are in alignment, we have the highest possible value, and when they are out of alignment, either in the x direction or in the y direction or in both directions, we can see that we get smaller values for this objective function. So all we need to do is essentially try and climb up this hill until we find the largest value, and that's when we say, okay, this is the transformation that we want to use. So, and obviously in most cases, the allowed transformation space is going to be much larger than two-dimensional. If you only have subject movement, for example, it's going to be six-dimensional. If you have things like eddy current induced fields, it's going to be even larger than that. And if you have something like topup, you know, it's a 1,000-dimensional space. But the principle is exactly the same. What you need is a set of allowed transformation, a space of allowed transformation, and a cost function that allows you to assess when you have found the best possible matching or registration of the two images. Now, the problem with diffusion-weighted images is that they're not easy to register. And the reason they're not easy to register is that they don't look the same. If you look at this image here, you can see that the different images look very, very different. So how do we find a cost function such that when they are aligned, we can maximize that? And the other thing is that, you know, all of these images are distorted, or they have movements in them. Let's say distorted in this case. They're all distorted, but they're all distorted in different ways. So we don't actually have a image that is non-distorted. So what is the reference image? I mean, what is it we're registering to? So these are the problems. I'm now going to explain how eddy works to sort of circumvent these problems. But first of all, I need to introduce you to Zoltar, the prediction maker. And what he is, so he's really a Gaussian process. And what you do with it is you don't cross his palm with silver. Instead, you feed him data. So you take all your diffusion-weighted images and you feed into Zoltar. Then you ask Zoltar to make predictions. So what we have here is we have the first diffusion-weighted image with a diffusion gradient 1, 0, 0, and then another gradient, another gradient, another gradient. All of this had been fed into Zoltar. We now ask Zoltar, okay, so what is your prediction? What do you think that the diffusion-weighted image with diffusion gradient 1, 0, 0 should look like? And importantly, the prediction is not identical to what was actually put in with that diffusion gradient. I'm going to come back to exactly how Zoltar works and exactly what he is. As I said, he's a Gaussian process already. But what I'm going to do is I'm going to tell you how I could have implemented Zoltar, but for various practical reasons I didn't. So one way to implement Zoltar would be to say that for every diffusion gradient that I put in, I also have to put in the negations. If I put in 1, 0, 0, I also have to put in minus 1, 0, 0. And that means I have two images with the same diffusion, well, with the same information content from a diffusion perspective, but with the diffusion gradients go in completely opposite directions. So I would expect that the distortions would also go in completely opposite directions. So let's say, so as I said, this is not how it works, but I could have made it work like this. So I've got 1, 0, 0, minus 1, 0, 0, put them into Zoltar, and Zoltar will give me as a prediction out for 1, 0, 0, the average of those two images. Now that average will be a blurred average because obviously the distortions go in different directions. So it will be a blurred image, but which is sort of in undistorted space because it's an average of two images that have been distorted in opposite directions. So then what I can do is I can use that to try and register it. So that would have been one way I could have done it. Another way I could have done it would have been to say that, okay, for each input image, I need to have another input image with exactly the same diffusion gradient, but acquired with opposing phase encode direction. And you remember from topup, that means that the distortions go in the opposite direction, and I could have used that in exactly the same way and just had the prediction be the average of those two images. Now, the reason I didn't do this is that it would have been a bit crazy to force people to duplicate every diffusion gradient, because from a perspective of diffusion, they don't contain any new information. And therefore, it would have been wasteful to force people or to assume that everyone would acquire every diffusion image twice, but with either opposing diffusion gradients or opposing phase encode directions. So that's why it's not done in that way. But as we go for the next few slides, you can think of it like that. You can think of the prediction being a blurred image in an average space of two images that have been distorted in opposite direction. Right, so now how eddy works. So first we have a loading step. And how that works is you pick the first diffusion weighted image, you use the current estimates of susceptibility and eddy currents and motion parameters. And for the first iteration, the susceptibility image is susceptibility induced field is the field that you have estimated using topup and then fed into eddy. The first estimate of the eddy current field is 0, because you don't know what it is, so you're just going to say 0. And the first estimate for the motion parameters is that they're all 0, i.e. the subject lays still. So you then use these to correct the image. So you are now in a sort of semi-corrected space, and you load that into the prediction maker, into Zoltar. And then you do the same thing for the second image until we have loaded all the diffusion weighted images. So now we have all the diffusion weighted images in there. They're corrected for susceptibility only, not for eddy currents and motion parameters so far, because they were all estimated to be 0. Then what we do is we start to get the predictions out. So we draw a prediction for the first diffusion weighted image. And remember, this is now not identical to the image that was input with this diffusion gradient, because it is a combination of all the different images that you put in, that all are distorted in different way in different directions. And as I said before, you can think of it as being the average of two images that's been distorted in opposite directions. Then we use the current estimate of susceptibility, eddy currents and motion parameters to get the prediction back into observation space, and then we compare that to the actual observation. And it's the difference between these two images that drives the registration, i.e. we have to work with the sum of square differences between these two images, and we'll repeat the same for the next DWI, etc. So all of eddy works like this. For all the scans, for all your different diffusion weighted images, you use the susceptibility field and the current estimates of eddy currents and movement to unwarp them, and you load them into the prediction maker. Then you have completed the loading stage. After that, for all the scans, you get the predictions out, you invert the current transform, you get the prediction in scan space, you compare that to the actual scan, and you use that difference to update your estimates of the eddy currents and the motion parameters for that particular diffusion image. And when you've done that for all scan, then you have completed the estimation step. And that's one iteration. So one iteration is going through the loading step and the estimation step. And then you go back for a second iteration, for a third iteration, for a fourth iteration, for as many iterations as you want. Right, so let's get back to Zoltar, because I'm assuming you're a little bit confused by him. So what he really is a Gaussian process. And what a Gaussian process is, it is a non-model driven estimation or prediction of what the data points should really be. So the way to interpret this figure you see here, so you've got the 0 point in the middle here, and then for a given diffusion gradient direction, you go in that direction until you find the point, and that's the data point. And the same way, if you go in that direction along here until you find this grey surface, that is the prediction that is made by Zoltar. Now, what a Gaussian process, how a Gaussian process works, is simply assumes, and it is a very general assumption, it simply assumes that nearby points, and what we mean by nearby points are points that have a small angle between them. Nearby points are points with a small angle between them. They should have a similar intensity value, and that's all there is. And this is implemented through something called a covariance function. And a covariance function is a very general function that simply enforces this smoothness on the surface. And compared to, for example, a tensor model or some other things, it's not biologically informed model, which means that there are no biologically meaningful parameters that come out of it. But it is very fast to estimate. It can model any anatomy. So, for example, here what we have here is a voxel with 1, 2, and there's actually a third crossing fiber, which means that the data point is not modeled well by a diffusion tensor at all. And despite this, presumably quite complicated looking shape, we can actually calculate these predictions using a Gaussian process much faster than we can a tensor. And as you realize, because we are doing this iteratively, iteration after iteration, doing all these predictions, it's important that it is fast. It can model multi-shell data, which is again another advantage. There are no hidden parameters. All the parameters are estimated directly from the data. There's only a handful of parameters that parameterize these covariance functions. They are estimated directly from the data. And importantly, very importantly, it allows us to do the pre-processing without assuming anything about the subsequent modeling. If we had a biologically informed model here, we would have biased all through our pre-processing, and have biased our data towards that model, that particular biologically informed model, for all the subsequent steps, and that's not something we want to do. Okay, and that was how eddy and topup works. And then for the next talk, I'm going to show you the practicalities, i.e. how do you actually go about running eddy and topup on your data. And please tune in for that. Thank you very much.